Welcome back to NE 630, Nuclear Reactor Theory. So we have been continuing the business of finding the flux distribution in the nuclear reactors. And last time we concluded the part for this thermal energy region, and we showed that it is a Maxwellian, modified Maxwellian, and the Maxwellian was modified by three things. The first thing is absorption at low energy, and we have to define a temperature based on the neutron. We call it neutron temperature instead of just the medium or the moderator temperature. And we give a Tn description for the Maxwellian. And the second part is the leakage term, and we said that we will change the sigma absorption, and we will substitute with sigma absorption plus d b square. And the last part, did anybody remember what's the last part in modifying the Maxwellian? It is where the joint function where the Maxwellian meets the 1 over E, and we represented this by lambda delta of T over E over KT divided by E. And we said that if the energy is greater than 10 KT, the delta function will be 1, and if the energy is less than 5 KT, the delta function is 0, and in between it will have certain form or certain variation. So the only thing that's still remaining in this chapter, it will be around 2 lectures today, and the next lecture will be how to calculate the flux in the presence of the resonance region, because this is very important. When you design the nuclear reactor, usually if you will solve you start with cell calculation, which is just you got the unit cell that I showed to you last time. So you have, let's say, a research reactor, and it is cylindrical in shape. So you will say, okay, around the fuel rod, I will put something like a circle, imaginary circle, and I will pick up the fuel rod and then some of the moderator around it. And I said this is the unit cell for the fuel. You will come to the one next to the control rod, for example, and you said, okay, take a different cell here in this region. There is another cell near the border, which the leakage will be more important, and so on. So you will take different cells, and then you homogenize, and you will get something like homogenized region inside the reactor. So where you will have fuel, you will have sigma absorption, sigma fission, nu, and so on, d, and so on. And then you will solve the multi-group diffusion equation. So again, to solve the multi-group diffusion equation, you have to get the weighting functions for the flux in order to get those multi-group constants. So in order to evaluate the multi-group constants, you have to evaluate those on the fast region, intermediate region, and thermal region. And what's important in the intermediate region is the resonance, of course, because you want to calculate what's the sigma absorption and resonance, what are the flux and resonance. And this will be the last part here to evaluate what is the flux shape in the resonance region. Of course, so this is just elementary manipulation. And once you did this and you solve the multi-group diffusion equation, you will get you will solve it through what we call finite difference scheme. So you will start with, let's say, an initial guess for the flux. You will get the second value. You will use the second value for calculating the group constant again, and then you will solve, and then you will get an updated value for the flux. Use it to get the, let's say, improve the group constants. Then you will solve the diffusion equation, get the third value of the flux, and then calculate the group constants again, and then use it to solve the equation, and so on until you find the final solution. You approach to the final solution, and this is usually the solution for using what we call, the first one is called cell calculation, the second one is called core calculation. And the core calculation is by solving this diffusion equation. Of course, you can solve, instead of all this hassle, you can solve the, instead of deterministic, this coded method is called deterministic solutions. You can solve, instead of the deterministic solution, you can solve the probabilistic method, which is based on Monte Carlo, for example, Monte Carlo MCNB. Or you can, in the deterministic solution, you can solve, instead of the diffusion equation, you can solve the transport equation. And transport equation has some techniques to solve, like the discrete ordinate or the PN and probabilities method and so on. So today we will just focus on doing the business, the same business, but for the resonance absorption. So let me start here by defining the resonance absorption. So we will define some parameters in the resonance region before we go ahead and calculate the flux. So just to remind you is the resonance cross-section and where is the resonance coming from and so on. If you remember in the 4NE 405, 495, which is the nuclear introduction to nuclear engineering, or any nuclear physics course, you will notice that we will have light A material, or what we call them light nuclei. Then we have intermediate nuclei. Then we have our heavy nuclei. Let's assume that this is the ground state, ground level, and this is the ground level. So the nucleus one of the models that represent or describe the atomic nucleus is, one of them is called the shell model. So there is a liquid drop model, there is a shell model, there is collective models. Each one of those models has success and failure, and it is very successful in describing phenomena, and it fails in describing others. For example, if you want to describe, for example, how the magic nuclei will behave, for example, in absorption, absorbing neutrons and so on, it's better understood under the shell model. The liquid drop model will give you some other properties of the nucleus that's perfectly fine and perfectly interpreted using the liquid drop model. So you will look at the nucleus as a liquid drop. So it has a surface tension and it has forces in between the molecules of the water inside it, and this is how you look at the nucleus. So if we look at the nucleus from the shell model, so the shell model will be similar to the electronic shells around the atom or the nucleus, but with a major difference. The difference between the shell model, atomic shell model, and the nuclear shell model is the following. In atomic shell model, it costs you less energy to raise the electron from the ground state to the first, then to the second, then to the third, seventh, then you ionize it. So this will cost you less energy than if you will raise a group of electrons at once from one level to the other. But in the shell model, it's easier to raise a group of nucleons from one level. The energy will be shared among all the nucleons and raise them to, let's say, a certain energy level, more than just giving the energy to single nucleon and then keep bumping it up in energy until you take it off from the nucleus. So this is one of the differences between the shell model for the nucleus and the shell model for the atom. So if we look at the light nuclei, the ground state will be here, for example. Then we will have the first. Let's say this is the first level, and so on until let's say this is one at, let's say, 100 kilo electron volt or so. So they are spaced apart, and they are few levels for the light nuclei. So if you look at, for example, something like helium, lithium, light nuclei, you will notice that the levels are not condensed level, and they are separated far away from each other. There is gaps in between, so big gaps in between. If you look at the intermediate one, for example, you will notice that you have something like 10 kilo electron volt, for example, and then you have more, let's say, more of those, and this is the 100 kilo electron volt, for example, more of those. If you look at the heavy nuclei, you will notice that the energy level are very, near to each other, and they start at very low energy, and they are very, very condensed. This is why the resonance happen when the nucleus will absorb a neutron, and the neutron will deposit inside the nucleus the binding energy of this nucleon plus the kinetic energy that came with it before the collision. So if you have a nucleus and then a neutron here coming with a kinetic energy, it gets in, it will open the door, knock open the door, get in, then close, then it will release the energy. So this energy is two things. One is the kinetic energy, because you come from movement to rest, and the other one is what? Is the binding energy. So if those two will coincide with one of those energy level, the nucleus will be excited to this energy level, and this will be a resonance cross-section. So this is why, for example, the inelastic scattering is coming from where? The inelastic scattering. So the inelastic scattering is coming from the fact that you have a neutron that gets inside the nucleus, then it will give the nucleus what? Energy. It will be excited, then it will leave. Okay, with different energy. It will leave the nucleus excited with different energy. This is why in nuclear reactors, the inelastic is not feasible for light nuclei, because the first, let's say, the first excited energy in the light nuclei at hundreds of kiloelectron volt. So light nuclei do not contribute to inelastic scattering. The most important in inelastic scattering is what? Is heavy nuclei. So, and at high energy, light nuclei can represent what? A big portion of inelastic scattering. Why? Because if you have 100 kiloelectron volt, for example, maybe you will have inelastic scattering. But as long as your energy is small, all the scattering is coming from what? Elastic scattering, but not from inelastic scattering. Did you understand this, guys? So if you will see here, for example, for one of those light nuclei, maybe you will have something like a cross-section like this, then you have a separated resonance, single resonance like this, for example. This is the energy, and this is the cross-section as a function of energy. But if you look at the heavy nuclei, you will notice that the cross-section maybe goes like this, then at 1 electron volt, up to 10 kilo electron volt, you will notice that you will have this highly unresolved resonance. What does it mean, unresolved? You cannot differentiate and separate them. This one is a resolved resonance. It's alone, standing alone. This is unresolved. This is resolved. This is heavy nuclei. This is light nuclei. And usually, this single resonance will be at, let's say, kilo electron volt and above. But for heavy nuclei, it will be from 1 to 10 kilo electron volt. So you have to keep this in mind. If you remember from the first lecture, or not the first lecture, the first chapter, we said that sigma gamma, or the radiative capture cross-section, meaning that you absorb the neutron and then you emit just gamma rays as a function of energy and temperature, was given by the Bright-Wigner formula. And this is sigma naught, which is the energy of the isolated resonance, E naught here, and multiplied by gamma divided by gamma. What's gamma? Do you remember what's gamma? Multiplied by E naught over the energy E, all raised to the power of half. Anybody and still remember? Yeah, but what's gamma? Yeah, it's the width, not the full width. Yeah, it's the full width at half maximum. It's called the radiative capture width. Okay, and gamma is the total width. So gamma over gamma is the probability that you will, if you will form a compound nucleus, you will decay by radiative capture. Okay, guys, and why we have temperature here? And this is sigma scattering, Why we have temperature here? Sigma naught, gamma scattering, gamma n over gamma multiplied by psi of xc and x plus sigma naught r over lambda multiplied by chi of xc and x plus 4 pi r square. If you remember, this was the shape scattering because of the shape of the nucleus, and this was because of what? Isolated resonance, and this was the interaction between the first term and third term. I stated this in the first lecture, or first few lecture, and I showed to you that xi of z and x is just data over 2 square root of pi. If you return back to chapter 1, you will see this. E to the power of minus 1/4 x minus y to the power of square xc square, and this is dy by 1 over y square, and alpha of xz and x is just xz over square root of pi multiplied by negative infinity to infinity e to the power minus 1/4. So I give you this at the very early lecture when we started. 1 second. Then x is just 2 multiplied by e minus e naught divided by gamma, and this xz is just gamma divided by 4 square root of e naught kt over a all to the power of half. Yes?
Wasn't that by your sigma naught over lambda? The R?
What?
Sigma naught over lambda.
What is sigma naught over lambda?
Right. What?
This one?
What's that to the right of it? Just to the right.
Sorry.
No,
Just to the right.
And then sigma naught was.
That one, yeah.
This one?
Yeah.
R.
Uh,
Sigma naught r, the radius. And again, I told you that this is interaction between this term and this term. Okay, guys? So, again, the temperature here, R is the radius of the nucleus. The temperature here, if you return back to your lecture notes or to the book at the chapter number 1, the temperature here is because of the fact that when we calculate the cross-section, the nucleus is moving. Yes? So we have to include the distribution of the nuclei in the medium, and the nuclei in the medium, if they are at temperature T, they will be distributed by a Maxwellian distribution, for example, as a function of T. So when you have this Maxwellian distribution, and then you will integrate over this Maxwellian distribution, you will end up with what? With the temperature T. So if you integrate over all the velocities of the mediums, because there is interaction between the neutron velocity and the nucleus velocity, and if you integrate over this, the nuclei velocity is given by a Maxwellian distribution. If you integrate over the Maxwellian distribution for those particles, you will eliminate the velocity dependent of the nuclei, and you will end up with just the temperature as a constant. So this is why the temperature is shown here. So now, why we are saying this? Because if you look at this process, if the medium is at absolute 0, so the nuclei will be at rest. So the neutron, when it comes, it will see dead bodies standing like this. So it will just hit the nuclei, or the standing sharks will hit them, and the shark will not say anything. Will say, just slam me and I will not say anything. But if you start giving some excitation energy to the medium, the shark will start a little bit moving, but will not be able to slam the neutron back and move. Until you give them a very high energy, then they will start moving and eating the small fish, which is the neutron in this case. So this is just like what's going on with energy. So so now the relative speed between the nucleus and the neutron at low energy has a very profound impact on the shape of this cross section. Okay, guys. So if we look at the cross section as a function of temperature, as let's say isolated isolated resonance. So it will be like this. So this is the sigma as a function of energy E and T, and this is the energy E. Then let's say the Bright-Wigner formula, we have an isolated cross section like this, and this is called the and we said that we have the flux will be doing what? Yes, and this is the asymptotic flux, which is 1 over E in the slowing down region. Once you come closer to the resonance, you will dip the flux because 1 over sigma absorption of E plus sigma scattering of E. Do you remember this? And this is energy self-shielding. So if you increase the temperature, what will happen? If you increase the temperature, this curve for the cross-section will broaden. So this is at T1, and this is at T2, and then increase the temperature again, and this is at T3, where T3 is greater than T2 is greater than T1. So as you increase the temperature, the value of the cross-section at the resonance will do what? Will go down. Sigma naught will go down. This is sigma naught at T1, sigma naught at T2, and this is sigma naught at T3. And sigma will go down. Sigma naught at T1 is greater than sigma naught at T2 is greater than sigma naught at T3. So the value for the cross-section goes down at the resonance at E naught, but the total area under the curve stay constant, because yes, you reduce the height, but you smear it out. So the total area will be the same. So this is called Doppler broadening. It's exactly the same like what? Like the phenomena in light, and also the phenomena in sound. Yes, so when you have a train coming to you, when the train is far away, you will hear a very faint sound. When it approaches you, the sound will increase. When it passes you, the sound will start decrease again. So the frequency is increasing while it's approaching you and decreasing while it's retarding from you. So the light, again, the redshift is the frequency will retard once the stars will be retarding from us. This is why the light coming from the star will go to the lower frequency, and lower frequency will be towards the red light, and this is what's called the redshift. So if it's coming to us, the shift will be toward the violet and magenta light or violet light. Okay, so toward the violet light. So this is why this Doppler broadening is a well-known phenomenon. Again, it is the same here, and this plays an important role in the nuclear reactor. Why? Because what happened is the cross section here at higher temperature, the value for sigma naught dropped. Yes? What will happen for the flux? Flux will increase. Yes? So sigma multiplied by flux will increase. So the absorption will increase. Yes? Absorption increase meaning F equal to sigma absorption in the fuel divided by sigma absorption in the fuel plus sigma absorption in the moderator plus sigma absorption in non-fuel. Yes? And eta is just nu multiplied by sigma absorption, sigma fission in the fuel plus sigma absorption in the fuel. This phenomena takes place in the fuel. Yes? sigma absorption in the fuel increases, but the fission cross-section is still, the Doppler broadening for the fission cross-section is very negligible. Very negligible. So sigma absorption increases, so this eta term will do what? Will go down. So the K infinity will go down and your reactor will shut down. And this is what happened in this research reactor here. In our research reactor, the fuel has some hydrogenous material inside the fuel itself. So if you will pulse the reactor, for example, to 350 megawatt during the pulse, the temperature will increase so much. So two phenomena will happen. The first one is there will be a volume increase for the fuel that will affect the moderation a lot, and now you will lose moderation for the neutrons. And also because of the Doppler phenomena, because of the raised temperature of the fuel, the cross-section will go down, the absorption will go up, and the reactor will go subcritical in just no time. So this is one of the applications. Okay, guys? So now let's define the resonance integral. So this resonance integral that I always give you the formula from the last two homework, or the homework and midterm. So the resonance integral is just defined as I gamma, and this is just the total absorption per nuclei of the resonance absorber. And it is defined as sigma gamma as a function of energy E multiplied by the flux as a function of energy E dE. Because if this is multiplied by n, the number density of your nuclei, this will be the total absorption per unit volume. But because we divided by n, which is the number of nuclei, this will give us the total absorption per unit volume per nuclei. So this is the definition of the I gamma. Then let's look at the resonance escape probability. So we have to do a balance between absorption and moderation in one single resonance. So if we have a single resonance like this, we have to do a balance between absorption and moderation. So let's say whatever comes to you here will be what? No, what comes before the resonance. We define a parameter that describes the number of neutrons that slow down below certain energy. What's this? Slowing down. So let's say that this is the energy E naught, so the slowing down density will be Q naught. What does mean Q naught? Total number of neutrons slow down below energy Q naught, or at energy equal to or less than Q naught, yes, per centimeter cube per second. So if we want to do the resonance, the absorption probability, so the absorption probability is just, this is the resonance absorption probability, and it is equal to the probability resonance absorption probability is equal to I gamma, which is the resonance integral, multiplied by the number of resonance absorber nuclei divided by Q naught. So this is resonance absorber nuclei, and this is the slowing down. So all what we did is we said how many neutrons coming to the resonance, and we calculated how many neutrons absorbed in the resonance. We divide the number absorbed in the resonance by the number that comes to the resonance, and this will give us the resonance probability. So if we say we have 1,000,000 neutron reaching to this single resonance, 100,000 of those will absorb it in the resonance. So what's the resonance probability now? Resonance absorption probability 10%. Yes, 10% of your neutrons will be absorbed in the resonance. So what's Q naught from last lectures? Xc sigma scattering multiplied by what? Energy E multiplied by what? Asymptotic cross section. And again, I told you that asymptotic cross section, asymptotic flux is just a flux far away from what? Far away from what? From the resonance. This is the asymptotic, phi asymptotic. So this is the value of the asymptotic. Yes, because you need the what? You need the slowing down coming before the resonance, away from the resonance to give you the slowing down. So you have to look at the asymptotic. Because if you come closer to the resonance, this is not the true value for the flux. The flux is depressed because of the presence of the resonance. So this is why we put the phi asymptotic. And phi asymptotic goes like what? What? Yeah, it goes like 1 over E. So substitute here, and you will get Q naught equal to what? Xc sigma scattering multiplied by E and some constant over E. Yes? So this will go as what? With this, and approximately this will be Xc sigma scattering. And the resonance absorption probability, which is I multiplied by N resonance over Q, will be I N resonance divided by Q, and Q is just Xc sigma scattering. So sigma scattering Xc sigma scattering is what? Is the moderation what? Moderation power. So what's the resonance probability then? Resonance escape probability? This is the absorption probability. So what's the resonance probability? Resonance escape. So 1 minus R absorption. So this will give you what? 1 minus what? I in Xc sigma scattering. And now for small value, for a small value, this can be written as for a small value, this can be written as e to the power of minus I in resonance divided by Xc sigma scattering. Why? Because if you have e to the power of x for a small value of x, this is nearly 1 minus x. Expand e to the power of x. This will give you what? 1 plus x plus x squared divided by 2 plus x cubed divided by factorial of 3 plus x4 over factorial of 4 and so on for a small value of x. As you raise it to the power, it will be very small compared to the x, so you can just eliminate all the higher order term and you will end up with e to the power of x equal to 1 plus x, or e to the power of minus x will be equal to 1 minus x. This is just and we can define the effective scattering, cross section pair resonance as the following. So sigma scattering effective multiplied by n resonance, the number of nuclei from the resonance, is just equal to n resonance multiplied by sigma scattering for the resonance nuclei plus n moderator for the moderator nuclei multiplied by sigma scattering for the moderator nuclei. So it's just averaging process. Yes? So we can just divide this by n resonance and this will give us sigma scattering. This is the effective resonance cross-section pair resonance nuclei. So if you have, imagine you have, instead of just one isolated resonance, you have resolved resonances. Resolved resonances. So sigma as a function of E, your energy like this, then you have the first resonance, then second resonance, then third resonance, and so on. So if you are coming from here, the neutron, if it has a chance or probability to be absorbed in this resonance, then it will pass it, so it will get another chance to pass this one, then another third chance to get this one. The more resonance, isolated resonance you will have, the less a chance that you will make it to the end here. Yes? And you knew from probability that if I told you what's the probability when you throw the die, so you have a dice, and I told you throw the dice once, what's the probability of getting 2? 1/6. What's the probability if I throw it twice to get 2? 1/6 times 1/6, so it will be 1/36. If you want to do it 10 times, it will be 1/6 to the power of 10. Yes? And this is still the same. You have a resonance escape probability for the resonance number 1, resonance escape probability for the resonance number 2, resonance escape probability for the resonance number 3, and so on. So the final resonance probability will be just pi from I equal 1 to n of them multiplied, operated over pi. Yes? So it will be the multiplication of the resonance escape probabilities of each individual one of them. Yes, guys? And this will be equal to what? When you have an exponential function for the probability number 1 and an exponential function for 2 and probability function for 3, when you multiply e to the power of something, you will add the what? You add the argument. So this will be just e to the power of what? Minus 1 over xc sigma scattering, the summation of what? Of I, gamma I equal to 1 to n. Or let it I, summation over I. Okay, guys? So we are just, the only thing different here, the number of resonance nuclei is the same. Xc sigma scattering is the same for the same resonance absorber. Yes? The only thing will be what? The integration over the resonance itself. Whether the resonance is wide or whether the resonance is narrow. So this will be the only difference. Okay, guys? Guys, did you understand? Yes, go ahead.
So this exponential approximation Or is it?
Yeah, it's hold, yeah.
Okay.
To a good extent it hold if x, if this value is small, and usually it is small, this value. But we will see how this will affect flow. So we'll have two situations that we will study. One when the resonance is so big, so wide, and one when the resonance is so narrow. What should we do? So what's the difference if the resonance is narrow or if the resonance is wide? If the resonance is narrow, you have a pretty much good probability that you will escape. One collision will get you out of the resonance. But if the resonance is wide, so you get to the white whale instead of shark. So it will open its mouth like this, so it will eat all of you. Hopefully not. So this is a very, very small chance that none of you will escape from the mouth of the shark. Not the shark, the whale. Yes? But if it is something like a very small fish, so there is very little chance that it will bite any of you. So it's exactly the same. Okay, guys? So now let's look for and define what we call by practical width. So again, let's look for this picture again for sigma as a function of energy E and the energy E, and we have our resonance like this. So in the resonance, when I showed to you the formula for the cross section as a function of energy and temperature for scattering, I told you that it has three components. One is constant, which is 4 by r squared. Yes? And r is the nuclei radius. So the nuclei radius, if you give me certain isotope, I will tell you the radius is constant. So 4 by r squared is what? It's constant. So the cross section has some constant value. And this is far away from resonance. This is the constant value, which is given by 4 by r squared. In the resonance region, the cross section is given by the Bright-Wigner formula. Yes? And in between those two regions, I have interaction between what? Between the Bright-Wigner and the constant term here. Okay, guys? Okay? And this is far away from the resonance here. So we will define an energy range over which the cross-section is larger than the non-resonance part of the resonance. So we will define an energy range. The cross-section is very high. Let's define the resonance, this to be here, for example. So this energy range where, of course not here. Let's define it here. So the cross-section in this area is way greater than the non-resonance part of the resonance. So the Bright-Wigner formula define a practical width to be given by sigma naught, which is this value here, sigma naught, divided by 4 by r squared, which is this value here. So the ratio between sigma naught and 4 by r squared is defined as the practical width. So for low energy resonances, if the energy is low, so this E is low for this energy resonance and low energy resonance, sigma naught over 4 by r squared can be represented as let me give you the formula. So for low energy resonances, sigma naught over 4 pi r square is nearly equal to sigma naught over sigma p, and this is in the order of 10 to the power of 3. Okay, guys? So sigma p is coming from sigma potential, and sigma naught is this sigma naught. So this is potential or shape resonance. Okay? So the practical width at low energy is in the order of what? 1,000. In the order of what? 1,000. So the practical width is much larger than what? The natural width. Okay, guys? So the remaining is just the start of the neutron flux in the resonance. And it's better not to bother you. We have only 2 minutes. And I can start directly next lecture with this part. Then hopefully we will conclude next lecture with this section here. And then from the following lecture, we will start the new chapter about the how to do. So far, we did the neutron diffusion equation without any time dependent. Yes? So it will be solving the time dependent diffusion equation and trying to deduce the neutron kinetic equation. So we will show that next couple of lectures what's the neutron kinetic equation, how the neutron kinetic will look like when we will assume that our reactor has, you can separate the two, the flux can be represented. We knew that the flux, let's assume we have a core that's a slab. What's the flux in a slab? Cosine. What's the flux in a cylinder? In the Z is cosine, in the R is what? Bessel function. What's the shape in a sphere? Flux? It's this shine or cosine function, or the shine function, let's say. So the flux has a shape. If our nuclear reactor is so large so that the H over D, the dimension of the core over the diffusion, let's say diffusion, or H over L, or M, H over M, the migration length. So if H over M is small value, for example, what happens is if you have any perturbation in the core, the perturbation will propagate so quickly. And let's assume that you have a control rod here and your flux is cosine. Once you put the control rod, the cosine will be distorted at the position of the control rod. But because of the perturbation will propagate, your reactor will reshape itself again, taking into account that there is a distortion here. It will retake again the same shape of cosine. So this is called neutronically tight core. If your core is not neutronically tight, meaning that you have a huge diameter compared to the migration length or migration area, migration length, this means that the propagation will not, the disturbance will not propagate, and you will have the same distortion no matter what you will do. It will take long time to respond, and you will not reshape again. So this means that I cannot separate the two functions that represent the flux. I have a function that represents time and a function that represents what? Space. If my core will readapt and give me the same shape again, I can separate the flux as a function of position multiplied by a function of time. Then when you substitute this in the diffusion equation, the function of time will cancel out everywhere, and you will end up with just a function. Sorry, the function of position will cancel out, but you will end up with a formula that's only a function of what? A function of time. This is called the point kinetic equation. So it is as if you consider the whole reactor as a point that changes with time. And I am no longer interested in the change of shape of the flux, because I knew that when we studied the nuclear reactor, we knew that we have a first harmonic, or the fundamental and the harmonic. The harmonic die out, and the first shape is what? Either decrease or increase. The cosine will decrease. This is not true for the neutronically loosely coupled. So if it's neutronically loosely coupled, I cannot solve the neutron kinetic equation, and I have to solve the neutron spatial kinetic equation. So I have to have a spatial term included with the time term, and this is very complicated, and it is not studied here in any of the course. I don't know that there is any course for reactor dynamics that study the spatial kinetic equation. It's upper level courses. So next time we will start the neutron kinetic. Then we will. This is the short term time behavior. Then we will go on to the long term, which is burn up and xenon build up and stuff like this. Then we will conclude our semester by types of nuclear reactor. Have a wonderful time.